So our second speaker of this afternoon is Mai Yin from the University of Denver, and she will speak about the cycle structure of random parking functions.
Thank you very much. It's always a pleasure to be at the ALA. I've given several talks on parking functions at this venue, but hopefully this talk will have somewhat different flavor. First of all, let's remember what is a parking function. So parking functions and its variations have been studied by different people from different disciplines. So we are going to look at the classical version of parking functions. So what happens is that there is a one-way street. So again, this is the most classical version. So it's a one-way street, and then the spots are 1 through n lined up. And then we have a line of cars coming in one by one, and every car has a preferred spot. If the preferred spot is open, the car will just directly park. And if the spot is already occupied, then the car will try to park at the next available spot as soon as it finds one. And if there is not an available spot, the car will just leave the street. And if every car is able to park, then this is called a classical parking function. And for our talk, we will just concentrate on the classical version, but we are going to look at some harder questions to study in probability for this classical version. Okay, so so here is a picture that I just described, and then for n equals 1, so one spot, one car, the only possibility is that the preference of the car is 1. And then if n equals 2, then you can have preference 1, 1, so both cars prefer spot 1, or 1, 2, or 2, 1. Right? And then if n equals 3, then here are the 16 possibilities for the car preferences. And one thing you might have noticed is that the preference sequences are permutation invariant, and we will show you why in a minute. Okay, so if we have 2, 1, 2, and then 2, 2, 1, we also have 1, 2, 2. So if something is a parking function, then any of its permutation will also be a parking function. Okay. So let's see why permutation invariant is one of the guiding principles for parking functions. This is because the parking procedure we just described could be well understood using a pigeonhole principle. Because if you want it to be a parking function, then you can have at most one car prefer the last spot. Because if you have 2 cars that would prefer the last spot, then one car will definitely have to leave. And then similarly, you can have at most 2 cars prefer the next to last spot. And then writing it in an alternative way, this is a pigeonhole principle people can see. And then because of the pigeonhole principle did not depend on the order the cars come in, we see that it's permutation invariant. And then the number of parking functions happens to be n plus 1 to the power n minus 1, which is a very nice combinatorial number. And this tells us parking function is in 1-to-1 bijective correspondence with many other combinatorial objects that have been well studied in the literature, such as rooted trees and then brackets and so on. So then because it's permutation invariant, a natural question people want to ask is, what other permutation invariant combinatorial objects are there? And then here in this talk, I will just present 2 of them, and we are both very familiar with them, hopefully. One is mappings. So mappings just means that I have a map from 1 through n to 1 through n, no restrictions at all. So for n equals 1, we have 1 possibility, n equals 2, 2 to the 2, so 4 possibility, n equals 3, 3 pure possibilities. So 27, okay? And then the other thing that have been studied a lot is permutations. And then permutations, we know just permuting all the n digits. So it's always n factorial. And you might also wonder, okay, why mappings and permutations? Just because they are well studied. It's actually for another reason. The thing is that parking function is a subset of mappings because we are placing some restrictions on the mappings for them to be parking functions. And also every permutation, as you can see, is a parking function. So, so the parking function is a combinatorial object that sits in between permutations and mappings. And permutations and mappings are both well studied. In particular, their exact enumeration results and also their asymptotics starting from many decades ago. And then we were like, okay, can we also say something about parking functions? And in particular, asymptotically, are they more like mappings or are they more like permutations? Because it's a superset of one and a subset of the other. And the remainder of the talk will concentrate on a detailed study of one property related to parking functions, namely the cycle structure. And we are going to present results and try to see whether it's one or the other. So to understand the cycle structure, we need to introduce how we wanted to define the cycles. And this is done as usual through the digraph representation. So digraph representation is defined for mappings. And so as a result, also defined for parking functions and also permutations. So the way we do that is that we are just going to draw a directed edge from vertex I to vertex Fm of I or pi m of I or Sm of I. So for digraphs of mappings and parking functions and also permutations, it will consist of connected components, and each component will consist of a cycle with trees hanging from the cycle. And I will show you a picture in the next slide. And it has been well known that mappings have on average half as many cycles as permutations. And then also for permutations, all tree components are trivial because like every point will be on the cycle. Okay. So let's take a look at the picture. So this is a picture I simulated using Sage for parking functions. It's uniformly drawn from the set of parking functions on 20 vertices. So here we see it has 3 components, okay? And this component is a fixed point, and this component is a pair with one tree hanging from one of the vertices, and this one is more complicated. Okay? And then, okay, so we are going to talk about the cycle structure, but before that, let's do a very quick lit review. So for cycle structure, random permutations. This is not an exhaustive list, but I tried my best. So Goncharov has central limit theorem, and then the Rentis and Pipel has functional central limit theorem, which is one step deeper than the central limit theorem. And then there is also large deviation result, and also length of the longest cycle, and Pingman has studies on the Poisson-Dirichlet limit, which we also heard about earlier this week. And then there is a wonderful book by these 3 authors on Poisson limit theorem for small cycle counts, in addition to other topics. And then for random mappings, like many theorems have been done in parallel, but mappings are usually harder than permutations for some of these results, like Stepanov established central limit theorem, and then Hansen did functional central limit theorem, and then Huang had large deviation principle, and then also length of R's longest cycle, and David Aldous also studied Poisson-Dirichlet and Flageolet, our own Flageolet, and Olisto had Poisson limit theorem, and then because mappings, there could be cycle components consisting of trees. So some people also studied components, not just cycle components, but the bigger components. Okay, so what about parking functions? So one thing that makes parking function harder to study is because for mappings and permutations, they satisfy so-called exchangeability. So by exchangeability, I just mean that you can exchange any vertices in the digraph representation of your mappings and permutations. It will still be a digraph representation for mapping and permutation. But for parking function, because of the restriction, this is no longer true. So if you just randomly permute the vertices in the digraph representation, you might not arrive at a parking function anymore. And this makes studying these objects harder. However, if we permute the rooted trees, so if we permute each rooted tree together with its root, then we can show that it will still remain a parking function. So here I show you two pictures, digraph representation of parking function, which is a top plot, and the bottom plot is also a digraph representation of parking function. And while I permute these vertices, I'm permuting the vertices on the cycle together with the tree branches hanging from the cycle all together. So this will keep the structures somewhat. Okay, so now let me show you some exact enumerative results. So here is a result for number of parking functions of length n with k cyclic points, and they are given exactly by this formula. So what is a cyclic point? Cyclic point just means it's any point that lies on the cycle of a parking function. And then fixed points are considered to be cyclic points, but having one fixed point is not the same as having one cyclic point, because it could be that you have more pairs and so on. And then instead of showing a proof for this formula to derive it took a long while, several pages. Like I will show you a related result and also a proof for that related result. Okay. So this is a related result I wanted to show you, and it appeared in the paper from me and Martin Ruby like a year ago. So this tells you the number of parking functions with k fixed points. So again, k fixed points is not the same as k cyclic points. Even though the formula looks a bit longer, the proof is actually easier. So I'm going to show you an outline of this proof. So here is an outline. Actually, we just need to use inclusion-exclusion property to do this, because k fixed points means I'm writing down the sets. AK just means what I wrote down there. And then k fixed points means I'm choosing k from n, and I want them to be fixed points. And I also want to ensure all the other points are not fixed points. And then I use inclusion, exclusion to expand them. And then expanding them after that, I use parking function is permutation invariant. Then I relabel the vertices to pi 1 through pi k and pi k plus 1 through pi k plus l. So this step is done through permutation invariance. And then for shorthand notation, I denote this by ak plus l. And the last step is to use this ingenious argument from Pollack, which I've been using many different proofs on parking functions. So the idea is that, remember earlier we showed that number of parking functions on n vertices is n plus 1 to the power n minus 1. And then because it's a product, people know there must be some like independent structure related to that. And Pollack showed in 1960s, I remember, was that you can think about this parking on one way as parking on a circle. And then all the cars will be able to park if n plus 1 is left unoccupied. And every car will be able to park modulo n plus 1 by following that circle rotation. And using this argument, remember earlier we had K and L, so we just need to choose K plus L spots. And then every car independently has n plus 1 choices. And then for the remaining cars, the choices are like you can just choose any of them, and it's n minus k minus l remaining cars. And then out of all the preference sequences, 1 over n plus 1 of them are parking functions. And then you divide by k factorial l factorial, because we assumed earlier that pi1 is less than pi k plus 1 is less than pi k plus L. So we have a fixed order. And that's how we got this formula. And then the proof for k cyclic points also used inclusion exclusion, but then we will need to use some deeper theory from symmetric group, but like it's based on similar ideas. And the last step of this is to use the binomial theorem. So we put in the formula for AK plus L, and then we're just using the binomial theorem backwards, recognizing it's that and that constitutes a factor x plus y. Yeah. Okay, I hope the proof makes sense. After finding the exact results for the k cyclic points, the next question to study is what about its asymptotics? And then the asymptotics, here is a theorem. So this theorem, we just use Stirling approximation to show that as n goes to infinity, and then k scales as root n up to a by a scaling. So we said this number of cyclic points divided by root n, we call it the scaled number of cyclic points. Then it satisfies this Rayleigh-1 random distribution. And this distribution also showed up for random mappings, giving us more hope. It behaves like random mappings asymptotically. And then I will not give the details of proof. It's just the application of Stirling. But then Rayleigh-1 random variable is well studied, and then we could relate result to some of the known results and derive like higher moments of the scale number of random variable cyclic points. So it's given by this exact formula, and the gamma is just the gamma function. Okay, and then after these asymptotics, then the other question we wanted to know is what about like convergence, like law of large numbers, central limit theorem, and also large deviation, and all these things. So we studied all of them. And then again, the crucial observation behind the proof is to utilize the fact that once we fix the number of cyclic points, then remember we are rotating, we are permuting the trees together with the cyclic points. So conditioning on the number of cyclic points, it's actually like a random permutation here. And then we let k sub 0 comma lambda n to be the number of cycles of uniform random permutation. And then, so yeah, what we do is that we first condition on the number of cyclic points, then we do a tower property. So that's how we study these things. And then through this technique, we were able to derive distribution of number of k cycles. So I will show you some results in a minute, but like in the results in particular, we will see this gamma coming up, and the gamma is the Euler-Mascheroni constant that has appeared in different contexts. So this is the expected value of the number of cycles in parking function, and it scales like log of n, and the variance also scales like log of n. And then the pi square appears from the Riemann zeta function. And then again, quick outline of proof. So the outline of proof first is that we need to remember how it's gamma defined, and in the proof, we are going to use two equivalent definitions of this Euler-Mascheroni constant. So one is that it's a limiting difference between the harmonic series and the natural logarithm. So we've seen the harmonic series coming up a lot this past week. Yeah, and here it comes up again. And it's also related to the derivative of the actual gamma function. That's why it's has this nice symbol, little gamma. And then once we know that, yeah, then we just utilize some results from random permutations in particular, Goncharov central limit theorem for random permutations. And this is the classical result. Then we do the conditioning argument. And then once we do the conditioning argument, like expected value is this, variance has 2 parts, and then we expand things, and then yeah, it will be done. Okay. And then so the rest is just calculation and simplification using some classical results from probability. Okay, so from here we can get to know law of large numbers. So it behaves like 1/2 log n in the limit, which is the same behavior as random mappings. And also we can get to know central limit theorem. So the mean is 1/2 log n, the variance is also 1/2 log n, also similar behavior as random mappings. And then also a deeper result is a large deviation principle. So we find that it has rate function I of x written here. And also, if you're not familiar with large deviation principle, here is a definition expanded. So we say that it satisfies large deviation principle, just means lim sup lim for open and closed sets respectively satisfy these properties. So I will not give the proof for law of large numbers and central limit theorem, but I will show quickly how we find this large deviation rate. So for the large deviation rate, we use Gardner-Ellis theorem, and then we did a Legendre differential transform to find that it's just calculating sup of this. And then the harder thing to calculate is this second component. And for the second component, we use Tower property. Again, in the end, we have this. People might have recognized this also. It was mentioned in the remark after Powell's talk just now. This is a Chinese restaurant process, Bernoulli 1/k. It also showed up in an earlier talk this week. So there are standard results on these. We just calculated them. And then so yeah, so gamma function showing up, and then you see the asymptotics of gamma function. You can find it on Wikipedia. That's how I found it. So, and then, yeah, calculations and then so on. Okay, so the last topic I wanted to talk about is length of longest cycle. So length of longest cycle just means like you count all the cycle lengths, and then you wanted to know longest and then second longest or r's longest. If there are fewer than r cycles, you define it to be 0. And then this is a result for the limiting joint density for number of cyclic points and the r's longest cycle. It satisfies this limit joint density. And this result is also based on a result. Actually, we utilize a result from Knuth and Trappado in the 1970s, I think. So they found that for uniform random permutations, this length of r's longest cycle is related to the generalized Dieckmann function written there. And then the generalized Dieckmann function is a generalized version of Dieckmann function, which appeared a lot in number theory. And then for that, they found that the length of r's longest cycle of uniformly random permutation is less than or equal to ny. The asymptotics goes to the r's Dieckmann function, 1/y. So we utilize that and together with power property, and we found that so yeah, conditioning again on the number of cyclic points. And then you see like here is L of Rk, not L of Rn, because now the cycle has k points on them. And then, yeah, so go passing to asymptotics. And then This is less than or equal to, so this is a marginal CDF. And then we do the differentiation, we will get the density. Okay. So last slide, I will just show you some asymptotics. So the asymptotics said that the expected value of the R's longest cycle roughly behaves like root pi over 2 GR1, and this is a Golomb-Dieckmann constant. So this is also similar behavior to random mappings. For random permutations, you don't have this root pi over 2. It's G of R1. And here are the definitions of these special functions. So there are many open questions for these cycle structure of random parking functions. If you are interested, I'm happy to chat more. I guess that's all. Thank you very much.